Welcome to this short recorded video on a short tutorial on classes and objects. This is in the prologue lecture for Module 4, and it's the first video that begins at the top of the lecture notebook. It's a good idea to run this first code cell that imports many of the packages and functions we will utilize within this lecture notebook. And we point out at the very beginning that you're already familiar with objects and classes. For instance, lists and NumPy arrays are objects. In fact, pretty much everything in Python, every variable is an object. This means we're in a good position at this point in the course to discuss some of the fundamentals of object-oriented programming, which involves the creation of classes and their instantiation. But what is a class and why are we doing this now? Well, we're about to start solving classes of problems, and when we solve classes of problems like root finding problems, numerical integration, optimization, and so on, you often find that you're generally setting up a lot of the same types of variables and using a lot of the same types of methods, and it's good to organize them in a single entity for best coding practices to make the code more readable and understandable and more well organized. So object-oriented programming is often referred to in short as OOP, and you could ask, what are objects in their relationship to classes? Well, this is from the wiki article. It's an analogy. You could consider two objects, apple and orange, as instantiations of the same class, which is fruit. So fruit is like the template of objects from which specific instantiations, like an apple and orange, belong. So they are inherently fruits, apple and orange, and it is guaranteed because they are fruits that you can effectively handle them in the same way. For example, from a programmer's perspective, you can expect the existence of some of the same attributes, such as color, or sugar content, or is ripe. Now, the data associated with these attributes may be very distinct for each instantiation, but the fact is, all fruit have some color, all fruit have some sugar content, and all fruit is either ripe or is not. And so you can have these different values for those variables for the different objects, but you would still have these attributes. If you abstract that a bit more, objects combine variables and functions, which are usually called data attributes and method attributes, and we'll return to that language below, into a single entity derived from a class. Classes are really nothing more than a template used to create your objects. I have a useful perspective here that you should read through. I'll skip over it in the video, but it's kind of looking ahead to what we do in Module 6 and how we can think about how we would approach something like a neural network. So how do we create our own classes and objects? Well, many classes like to create objects with instances customized to a specific initial state. In that case, a class may define a special method named init with 2 underscores on either side of it, and notice the parentheses. We show this below, and we often pass variables inside of that init as part of the initialization process. So this is an instantiation operation that is also known as an initialization function, thus the init. We use this below. It's not necessary, but it's a good idea to always have this, even if the initialization object does nothing, because it's a fairly standard way to write your class with some initialization. There's some other conventions that we use, and that we use the variable self almost everywhere within classes. This is in fact the first argument of any method defined within the class. It's nothing more than a convention. The name self actually has no special meaning to Python, but it allows for more clear readability of code and understanding of what in an object is essentially a self-referencing part of the class in terms of the data and method attributes that it's referencing. We will initially see that object is a variable parameter for a class declaration. So just scrolling down below, you'll see this is what I mean. It shows up here when we define a class and we have the name of the class and then we're passing object. Again, that actually is not necessary either, especially in recent versions of Python, but it is a convention and it's useful to distinguish a base class, also called a superclass, from a subclass. And we will discuss subclasses later in this notebook, and that will be in a separate video. Let's go ahead and dive into this with a silly example. So in this example, we create a class called I am what I am. It is instantiated with a single input variable that we call x. Now x could be anything. As you'll see below, and I'll just go ahead and scroll, I will instantiate it with a NumPy array. I will instantiate it as well, or instantiate the object. I do it with an array, but I also do lambda functions. You could do it with just about anything you want. So whatever that variable is, whether it's a function, referencing a function, a NumPy array, a list, I pass that to I am what I am, and then I create an object that knows a little bit more about that variable than maybe the variable itself. So this variable x becomes a data attribute. What I mean is when we instantiate, when we call the initialization function, we pass x, as you see here, and there's self as the first argument, and then self.x now stores x as that data attribute of the object. And it's referenced through the dot operation. So for instance, when I create the array A here, and then I create B as this instantiation of the object, right, that uses that variable A, you'll see that I use b.x because self.x is the name here. So x is always this variable, no matter what the variable name is that I'm passing for this object. That's just a placeholder. But here it's always self.x. We'll go through that example slowly. I'm just trying to prime you for what you're going to see. So the variable x becomes a data attribute, and it is accessible using the dot convention. The functions defined within the class are called method attributes. They are also accessible through the dot convention. If the idea of a data and method attribute being accessible through the dot convention seems strange, consider in NumPy arrays, we've seen that we have some data attributes like .shape and method attributes such as .min and .max. Now, the difference between a data attribute and a method attribute is that I don't have any parentheses here. Shape is not a function. It just holds data about the shape of an array when I have a NumPy array. Whereas .min and .max are functions and I need those parentheses. Every time we call a function or a method in Python, we need to use parentheses. So let's look at this object. I create the class, I am what I am, and it is an object. The instantiation of it defines an object. And again, having object there is unnecessary, but it's just a nice convention. I initialize that object with a variable x. I store that variable as the data attribute self.x. Then I have three separate method attributes where the object that has been instantiated, you can ask it, what am I? And it will print the type of the variable that was used to create it. And if you say, well, what actually created me? What created me? Then it will print the actual variable. And if you ask it its purpose, it just says a really bad joke. This is classified. So it's dad humor. And I apologize for how bad it is, but I couldn't think of another way to illustrate that you could have some really ridiculous functions here if you want. Okay, so I now run this code cell. I now create a variable A that is a NumPy array, and then I create this variable B that is this instantiation of this class using the variable A. Now, I can ask B, what am I? This attribute is a method. It's a function. It requires, again, the parentheses. If I say, what am I? It'll say, well, you're a NumPy array, an ND array. If I say, okay, but what actually created me? It's the variable 1, 2, 3. Notice what it did when it said what created me is it printed self.x. So it prints that 1, 2, 3. That is that array of A. And if I ask it my purpose, it says the bad joke. Now, the variable A is the data attribute x, right? So I pass a variable in here. Whatever it is and whatever its name is, it gets stored as the .x variable of the object. Self is just this placeholder, the self-referencing variable within the class template. But the class name, at least the instantiation of it here, is B. So I do b.x. It's a data attribute. I don't need the parentheses. And I can see, look, it's array 1, 2, 3, right? It looks just like this object A, or this array A that was used to create it. Now, here's something that's interesting. What happens if we change the array A? For instance, I take that third component, remember Python indexing starts at 0, and I make it a 7 instead of a 3. Now look at b.x. It's 1, 2, 7. Can you explain this? Well, you can think of mutable versus unmutable data types. So that's something to think about a little bit that I believe we saw in Module 3. Now, delete A from memory. If I delete A from memory and I ask to just access A, this returns an error. Well, A is not defined because I've deleted it from memory. But look at b.x. It's still there. So the system has some sort of memory. So this seems a little odd. I can change A, I can change components of it, and it changes the instantiation of the object that is B now. But if I delete A, B.X still persists. So what's going on? Deleting A is removing how A references the memory that is holding the array 127 in memory. It didn't actually delete the array, it deleted the variable A that references where the array is held in memory. But B is still referencing that same area in memory. So if all of that seems a little weird, and maybe you want your object to just be a little bit more stable, especially with respect to this operation, that if you change A, it shouldn't change the object that's already been instantiated, then you want to use the copy function. So there's some additional information for you to read here. I am just going to go ahead and show you how it works in this video. We're going to import copy, and now I'm going to create a new class that's a little bit more stable. It is I am what I am no matter what you say. It might be no matter what you say or do. And from copy, I'm going to use the deep copy function, and I'm going to copy that variable x into the data attribute x. Nothing else has changed. When I do that, and I have this array A, 1, 2, 3, I create B as I am what I am no matter what you say. And now I change the third component of A, that 3, to a 7. And now I look at B.X, it's still the array 1, 2, 3. So if you're dealing with mutable data types, and you might be changing those data types after you use them in the instantiation of an object, and they get stored as data attributes, and you want that to stay the same, even if you start reusing or redefining these variables in the other part of your code, you should be using the copy function. That's the short message here. So let's see something maybe a little bit more mind-bending. Here's f as a lambda function. It is the polynomial x squared plus 2. And now c is a instantiation of the class that has f. All right. What is c? C can ask, what am I? It's a function. You can say, what created me? It says a lambda function. And I can say, what is the actual attribute c.x? It says, it's just this main. It's hard to actually see what the function is at this point. But notice how these three different things are printed differently. What am I? Well, it printed the type. A lambda function is a type of a class function, so it says it's a function. If I ask what created me, it's just saying, what am I trying to print? Self.x. And then if I actually ask for self.x, I again just get this lambda function. Now, c.x is a data attribute. It's a data attribute because it is a function that was stored as the data attribute self.x. But it's a data attribute that is itself a function. So I can say c.x with no issue whatsoever. It says this is a function. But if now I can actually pass 2 to it, and it's just my data attribute happens to be a lambda function, a class of a function, and I can evaluate it at 2. And of course, if I evaluate it at 2, I should get 2 squared, 4 plus 2. This should give 6. So that's it. I have a data attribute.x, but that data attribute is itself a function. And so I can also basically access it with or without the parentheses. And if you've ever wondered what the difference between similar types of objects are, this class can help you determine that. Let's create a non-anonymous function that does the same thing as the lambda function above and make it more self-aware with our class. So here's a function, I call it test. It's the same thing, x squared plus 2. That's what it returns. But now let's look at D, which is I am what I am no matter what you say, but it uses test to instantiate it. If I ask what I am, still says class function, just like this one. But if I say what created me, it's a function, then it has the name test here, whereas this said this was a lambda function. So this is something that uses the definition of a function name, right? It's not an anonymous function. Lambda functions are meant to be these kind of anonymous, non-named functions. You can assign them names, but they're intended for you to not even have to do that. And then again, I can evaluate d.x of 2. And I could also look at what is d.x, and that's that function, test of x, right? And there's that dot test of x as opposed to just this anonymous lambda. It doesn't really ever care about this function name f. I'll just go ahead and change that back to dx of 2. Okay, I will have a separate video that goes over the solutions to this activity about a class of polynomials. I recommend you really read through this carefully and try to solve this on your own before looking at the solution video that will be posted on Canvas. This is a very useful exercise that has a good computational bent to it, and it starts making you think about how we're going to be using classes for the rest of Module 4. And below that, we'll talk about subclasses and superclasses, but that will be the subject of the next video. Thanks for listening.